Okay, so hydrogeology recorded lecture March 23rd. We'll be talking about unsaturated flow mostly, but also to start some homework question clarifications. So first question was on problem 6. And in part A, you're supposed to calculate the total discharge through the aquifer, and you don't have a K until part C. Use the K of part C to calculate the discharge for part A. The next question was on quick conditions, and we're going to lecture on those quick conditions here in just a second. Let's see, the third question was for these flow nets for problem 2. And in these flow nets, you're to assume that they're heterogeneous and that the wherever you have the speckled zone, it's the higher hydraulic conductivity. So in this upper figure, K1 is higher than K2 because it's speckled. And in the bottom figure, K1 is lower than K2 because K2 is speckled. Did I miss any questions that we asked? Okay, minor miracle. All right, so the next question that requires a bit of theory is quick conditions. So let's hit that real quick here. And really that, we'll just put that under flow net analysis here. Okay, and the basic idea of quick conditions in a nutshell is it's when the upward fluid pressure is high enough, the pressure gradient is high enough to float the sediment. So the upward fluid pressure floats sediment. So the grains are no longer sitting on top of each other, they're being held up by the fluid pressure. Okay, so let's just think about a force balance. For a little cube of porous media. And try to draw a decent cube of porous media here. All right, so here's our cube of porous media. Put some sediment in there. And it's got some length that we're just going to call L, some height. All right. And we're interested in the force balance on this cube, all right? And let's just say that it's a small cube. So L is really small. And we can think about the upward pressure. So let's say that we're able here to install a piezometer that comes down and measures the fluid pressure or the head at this point at the bottom of our cube. All right, and so we'll talk about what this head's going to look, what the measurement is, but we've got one piezometer, it's measuring the head at the bottom. And then we've got another piezometer measuring the head at the top. Sorry, let me redraw this. So another piezometer finished such that it measures the head at the top of the cube. All right. And we've got an upward fluid pressure. That's one of the things that we have to have quick conditions. We got to have an upward fluid pressure gradient. All right. So the head at the top of the cube is less than the head at the bottom. And let's call this height we'll call this H prime. And we're going to call the height from H prime to the top up here H. So that's this height right here is H. Okay, so now, I've got my cube thickness is L. The head height at the top of the cube is H prime, and the head or the increase in distance from the head at the top is this H measurement here. All right, so my force balance is going to say the upward force here is equal to the downward force in across my cube. Let me change the downward force here. So my upward force and my downward force are going to be equal. That basically just means my sediment's not moving. All right, so it's called static equilibrium, right? Things are not moving. All right, my upward force is given by the fluid pressure pushing on the base of this cube. So what is the equation for fluid pressure? It's rho G, and then it's the height of the water column above the point. So I want to calculate the fluid pressure at this point right here at the base of my cube. And let's let, the height H equals to 0 will be the bottom of my cube. So my pressure says P is equal to rho water G times the height of the water column above that point. So at point A, P sub A, my pressure is rho water G. And this H, if H is equal to 0 is the bottom of my cube, then my total height is L, the height of the cube, plus H prime plus H. Convince yourself of that. It's a little confusing, but bottom line is the height from here to here is equal to this height plus this height plus this height. I've just broken that total length into 3 pieces. I've done that for a reason. I could have defined some height, H double prime that goes from 0 up to the top of the water column. But I've just broken it up into its 3 pieces. L plus H prime plus H. All right. And then this would be multiplied by the area across which this is acting. So we'll just say the area at the base of the cube. All right, my downward forces in my cube. So this is upward. Good question. Great question. Why is gravity involved in there? I love the question, and it's not necessarily immediately intuitive. Okay, so you said a key word, upward pressure, right? How do we calculate pressure? Yes, so that's why G's in here. I want to know the pressure at this point. I need to know the density of water, rho W, G, and then the height of the water above that point. Now, you are correct that I am now going to consider my downward force, and gravity is going to come into effect there as well. So my downward force ooh, got a little dyslexia going here this morning. I'll put downward in a different color. I'll make it green. My downward force, I have two forces pulling the sediment down. One of them is the force of gravity pulling the sediment down. So that would be rho sediment times G times the volume of the sediment above this point. So that's the volume of the sediment would be L times A. All right, and this is gravity pulling the sediment down. All right. I also have the fluid pressure pushing down at the top of my cube. So that's rho water G. Now the height here to calculate this pressure is just this height. So that's H prime times A. All right, so upward, I've got, this is my upward force. These are my two downward forces. And at equilibrium, if my sediment is not moving, then they are equal to each other. So if sediment's not moving, or if we're at static equilibrium, upward equals downward. All right, so I'm just going to set these two equal to each other and then do some algebra. So my upward is rho water G times H plus H prime plus L. And my downward was rho S G times L plus the fluid pressure at the top of the cube, rho water, G times H prime. And each of these had an A multiplied by it. So there's an A, an A, and an A here, and those just cancel out. So I'm just going to get rid of the areas, if that's okay with people. Or I'll leave them here. I'll write them out, and then I'll cross them out so that you've got them in your notes. Okay. Now I'm just going to expand all these terms. I'm going to multiply them out, and then I'm going to collect like terms. So rho water GH plus rho water GH prime plus rho water GL is equal to rho S GL plus rho water GH prime. So these two cancel out. And I can collect these two. So I could get rho water GH is equal to rho water minus rho S times G times L. So all I did was move this over here, collect these terms. Both of these are multiplied by L, so now this gets back to Autumn's question. I have gravity working to push things up, and I have gravity working to push things down. So gravity is just going to cancel out here. So I get rid of those two. And then I'm going to let's see. I'm going to do just a little bit more movement here. So I'm going to divide L over here and bring rho water over here. So I'll get I've mixed these up here. I don't know if you guys noticed this, but I did now. Rho S is positive. If I'm going to subtract this over, I should have subtracted water over. All right, so I'm going to get rho S minus rho W over rho W. That's this coming over here is equal to H over L. All right. And this is equal to the critical hydraulic gradient. So this right here, this ratio is how you calculate the critical hydraulic gradient. This is the definition. If my head gradient is equal to this ratio, rho S minus rho W over rho W, then I have enough upward force to float my sediment. What's that? if my hydraulic gradient, if I crit my hydraulic gradient is equal to this value, whatever you get for rho S minus rho W over rho W, then I have enough upward force to float it. If it's less than that, I do not. If it's equal to or greater, I have enough. So if hydraulic gradient, which you get from your flow net, is greater than rho S minus rho W over rho W, then I have quick conditions. Fair. I like that attention to detail. So it's actually very simple. You got to figure out what your hydraulic gradient is. You can get that from your flow net, and you just got to compare it to this value here. Okay. So now let's shift gears. Oh, before we go any farther. All right, we're done talking for a sec about homework because we're going to move into another lecture topic. But before we move on, I wanted to talk schedule. All right, I have written here field trip 4-1. Let's just pull that up. That means we'd be taking a field trip on Thursday or something. I cannot take a field trip in the middle of the week. So that was just a mistake on my part. So I have written that we would do a field trip here. This would be, I have to teach other classes, so it's not going to happen for me. Can you guys do Saturday the 3rd? Autumn can. You're competing. Are you competing like every weekend for the rest of the? Yeah. So you'll just have to get the data. I don't really know. I can't do that Friday because we're doing some stuff for the department. Yeah, unfortunately, Saturday is kind of my only day. But what you can do is get the data. Okay, so I talked with Cam, my friend at the Montana Bureau of Mines and Geology. She can come out on that Saturday and we can go up to Lolo and we'll measure water table depths. We'll do some pump tests. We'll do some slug tests. And that data is what you're going to use then for your final project. That's kind of why I want to do it the 3rd, is so that we get that data as soon as possible so that we have it for the rest of the semester. So let's tentatively plan. Well, let's plan on the 3rd. And we'll leave at 8:30. And last time we were back by sort of afternoon, say 4-ish. So plan on a lunch out there. plan on the weather conditions being approximately horrible. Last time we did it, it was snaining at about a 12-degree angle. So that means the wind was blowing pretty good. We are hydrogeologists in Montana, and so we would never work if we can't handle a little bit of bad weather. So it's just the way it is. Bring eyewear. I'll tell you what I wear in the field. Been doing it a long time. I figured out what doesn't work and what does. I have a pair of hiking boots, waterproof hiking boots. I will, depending on the weather, I normally wear a pair of like synthetic soft shell pants. All right, so something that can get wet and I won't freeze when it gets wet. Wear some up top. I try not to wear any cotton. So I have like long underwear, either polypro or wool. And then I wear fleece or wool sweater. Bring rain jacket or rain pants. You can wear cotton pants, but bring rain pants if you do that. Bring a beanie, a warm hat, and bring a pair of gloves or mittens. And then I like to bring a ball cap for sun and sunglasses. Lunch and water. So we'll be up Lolo Pass. There's nowhere to grab lunch. So it'll be eat in the field kind of a thing. Make sure you have water. Bring something to write with. If you don't have one, I encourage everybody to get some kind of Write in the Rain field book. I'll have a handout for you. But you know, if you want to go on in geosciences, having a field book that's a Write in the Rain is always a good idea. They're not that expensive. They're at the bookstore. You can get a small one, whatever, but they're a good thing to have around. That's pretty much it. Bring a calculator. It's not always a good idea to have. I guess your phones are calculators now, so it doesn't really matter. I will have all the other equipment for measuring groundwater levels, groundwater pumps, all that stuff that we'll learn all about all that stuff. Okay, I think that's it. I don't think so. We do go check some water levels on staff gauges. And on a couple of those, we got to kind of pick our way to get to the actual creek, depending on how flooded it is. But we've never had to have waders. I'll talk a little bit with Cam about it, but so far we've been fine without them. I might throw a couple pairs in case somebody needs to go down there and it's real wet. All right. So for now, let's plan on the third field trip. Okay. Yeah. Yeah. Yeah, that's the critical hydraulic gradient. Your job is simply to compare the hydraulic gradient you have to that. Does that make sense? It's you're gonna get, like, for example, in the field, we measure a hydraulic gradient, or this flow net gives you the ability to calculate hydraulic gradients at a point. And then you compare that to the critical hydraulic gradient. Yeah. No. H is just that little bit at the top. Yeah. Oh, here's the bottom line. All we did is derive what the value. Okay, this is a good question. All we did is derive what the value of the critical hydraulic gradient is. So you calculate the critical hydraulic gradient with this equation, rho S minus rho W over rho W. This gives you the critical hydraulic gradient. So this is, for example, how no, you get the critical hydraulic gradient from this. You take, for example, we would take 2.67 grams per cc minus 1 grams per cc over 1 grams per cc. Right? This is approximately quarts, and this is water. Well, if I do the math, this equals 1.67, right? That's the value of a critical hydraulic gradient, 1.67. Now I just got to calculate what my hydraulic gradient is at a spot. Upward hydraulic gradient, critical. Is that equal or greater than 1.67? If it is, I have quick conditions. If it's less, I do not. All right, and 1.67 is a massive upward gradient. There's a reason why we don't often walk around and fall into quicksand, right? It happens very rarely. Only where there's a lot of groundwater discharge. Okay, are we clear on this? All right, let's start talking about pressure head near the water table. And let's, so recall that my total head, right, is equal to my elevation head plus pressure head, right? Total head is equal to the elevation plus the pressure head. So when we here's the land surface, here's the water table. So if I were to put a well in here or a piezometer, and it's finished right here, and here's some bottom datum, z equals to 0. All right, this would be z. This is the elevation head above this point, and this is psi, my pressure head at this point. Okay, so elevation head, pressure head. The total head is equal to the elevation head times the pressure head. Now, what I want to do is think about what happens to the pressure head near the water table. All right, so as I move, if I move the location of this well all the way up to the water table, what would my pressure head be? 0, right? At this point, I've got no elevation of water above my point. The water inside the well would go right to the bottom of the well, and all my head would be measured by Z, the elevation below the point. Now the question is, okay, what would happen if I finished a well right here above the water table? What is my pressure head above the water table? So does anybody know when I say gauge pressure, does anybody know what that means? What is gauge pressure? So let's define that right now. Gauge pressure relative to atmospheric pressure. Okay, so gauge pressure is pressure relative to atmospheric pressure. So we can think of our pressure head as basically a measurement of the gauge pressure of the water. So if I'm down here and I have atmospheric pressure inside my well, because the atmosphere is sitting here, then water will, the pressure, the fluid pressure here is greater than atmospheric pressure, and it will push into this well, all right, until sort of it'll push in until the fluid pressure inside the well is equal to whatever's pushing it in. So until those two come to equilibrium. So when gauge pressure is positive, the fluid pressure is higher than atmospheric, and it would tend to push water into the well. So below the water table, and let me call gauge pressure P sub G. All right, below the water table, psi is greater than 0, and we can think of psi as the gauge pressure. All right, so this is scenario 1. At the water table, let me write this out. Water table. At the water table, psi is equal to 0. That means my gauge pressure is equal to 0. And it basically means my pressure is equal to 1 atmosphere. Okay, now above the water table. So let's say that I had some water inside a tube that I stuck down into the ground above the water table, but it's sealed at the top, right? So it's got this gauge and it's sealed at the top. Like a straw, you know, I pick a straw up out of a soda drink and then I stuck it into the ground. What would happen is that, remember we talked about capillarity, how the water adheres to the soil, all right, and gets pulled into those capillary tubes. So what happens is if I stuck this thing and it was sealed at the top and it had water in it, water would get pulled out by the capillary action. So water gets pulled out. By capillary action. All right, we talked about that. That's the cohesion of the water to the sediment walls and to itself, and it tends to pull things up those tubes. In that case, if water is being pulled out of here, I will create a negative gauge pressure. So above the water table, psi is less than 0. That means my gauge pressure is less than 0. And this is because water gets pulled by capillary action. And it's this pulling. You'll often hear this in soil science. They call this tension. They want to know what the tension in the soil is. That's essentially how well does this soil try to pull water out of a tube full of water. Okay, so if I've got this setting where I've got, here's my land surface. Here's my water table. And I had a plot here of my pressure head. And this right here is 0. All right. I am equal to 0 at the height of my water table. That's the definition of the water table, where the pressure head is equal to 1 atmosphere, or where the fluid pressure is equal to 1 atmosphere, which means the gauge pressure and the pressure head are equal to 0. That's the definition of the water table. All right. Below that, my pressure head is negative. Or sorry, above that, my pressure head is negative. So in the vadose zone, my pressure head is negative. And once I reach the bottom of the water, or once I reach the water table and I start moving down, my pressure head increases with the height. So the water table is the zone where I move from negative pressure head to positive pressure head. So let's write out some basic rules below the water table. Both my elevation head and my pressure head are positive. And my total potential, or my total head, is equal to Z plus psi. At the water table, psi is equal to 0. That is the definition of the water table. Psi is equal to 0 here. So here, but Z is positive. So H is equal to Z. My head is equal to the elevation of the water table. Below the water table, psi is less than 0. Z is greater than 0. And so my head is equal to Z plus negative psi. Thank you, Autumn. Above. Above the water table, my pressure head is less than 0. So my head is equal to my elevation plus my negative pressure head. Yes, Z can be negative, but we're going to just say it actually doesn't matter. It can always be negative as long as it's always referenced to the same point. But usually the convention is we would have some Z below all of our water depths. We're just looking at relative changes in potential, and so it doesn't really matter, but by convention, Z's usually positive. Okay, let's talk about some other things that change. So first of all, let's think about let's just focus in a little bit on unsaturated porous media and think about what the fact that we have variable saturation does for our flow parameters. So here's a box. I'm going to put some grains in here. All right. Now, if we are not fully saturated, that means not all the pore space is full of water, right? So in that case, we might like think about how water is distributed in here, but we might have zones here where water fills the pores. And zones where air fills the pores. So some of my pore space is full of air, some of my pore space is full of water, right? Some observations about what we would look at if we were looking in a slice of porous media. One is that the amount of air, so let's say this is air here, and this is water in my pores. So one, the amount of water in pore space varies. And we already calculated some of these things, but we have a way to measure the amount of water in the pore space. Does anybody remember what that was? What a measurement of the amount of water in the pore space was? We had a few different ones. So that was mass wetness, right? We could, the mass of water to the total mass of the sediments. What was volumetric water content? You guys remember what that was? It got this symbol theta sub W. And it's equal to the volume of water over the total volume of porous media. What's the maximum that volumetric water content can have? Well, can my volume, if I'm in a porous media, can my volume of water be equal to 1? Right? It can, the most I can have is all my pore space full of water. So this varies between 0 to N. Another important thing is that the distribution of water is not uniform. And if we sort of recall, let's do you remember we talked about the height of the capillary rise? That it means how, that's a measure. The height of the capillary rise is a measure of how well your soil will pull water into it. And it got this 2 gamma cos theta over rho GR. And this was water tension, water surface tension. This is how well water clings to itself. This was the contact angle. This is how well water adheres to the soil. Or sticks to the soil. So these two are basically, roughly the same. All soil materials are They're not exactly the same, but they're made out of basically the same stuff. And turns out that water surface tension, it's a function of temperature, but it's basically a constant. And the cosine of theta is basically a constant. All right. The thing that really varies in a soil is this, the pore throat radius. And what this equation tells me is that the smaller the pore throat radius, the higher the capillary rise, or the stronger the water will be pulled into the sediment. So smaller pore throat radiuses have large tension. They have a greater ability to pull water into the pore throat. Okay, some direct effects of this distribution of water. If I want to move water through this porous media, so if I'm transporting water through this porous media now, and I do have unsaturated flow, all right? If I did not have unsaturated flow, I would never be able to drain my field when I irrigate it, right? Water moves through unsaturated soil all the time. If I want to move water through unsaturated media, it has a smaller volume of that unsaturated media to move through it. By definition, not all my pore space is full of water. I have less area through which my water is moving. So lower saturation or lower amounts of water, lower volumetric water content means less area for flow. All right, the less pore space is full of water, the less volume there is to accommodate fluid flow. That's just the way it is. The other thing is that the lower the volumetric water content, the pores that hold on to the water the best are the smaller pores. And this is really important. That this drives two things. The lower my volumetric water content, I'm moving water through less pore space and smaller pores. All right. What do we know about smaller pores? Do they have higher or lower permeability? Is it easier or harder to move water through small pore throats? Harder. Yeah, they're smaller. You got to push really hard to move them through small ones. So what do you think happens to the hydraulic conductivity of a porous media at lower saturation? It's going to be lower, right? I'm moving through smaller pore throats and I have lower area through which to move it. So hydraulic conductivity is reduced at lower. These two things mean K is lower with lower beta sub W. I gotta stop my video because that's killing my power. All right. The next thing that happens here is that, so here's how we deal with that. We come up with this idea of relative hydraulic conductivity. And the idea is that we write, so K sub R is a function of my volumetric water content. And it varies between 0 and 1. And the lower my water content gets, the lower my relative hydraulic conductivity gets. And I write the hydraulic conductivity of my sediment as K sub R times K sat. That's my saturated hydraulic conductivity. That's the hydraulic conductivity that we've always talked about for groundwater flow because we're in the saturated zone. So I take this K sat, I multiply it by this K sub R, and I'm going to get the true or the effective hydraulic conductivity. We call this K effective, is the effective hydraulic conductivity for my unsaturated material. So as soon as I'm become unsaturated, my K sub R goes less than 1. All right. And my saturated and my effective hydraulic conductivity is less than my fully saturated hydraulic conductivity. So the key point here is that the maximum my hydraulic conductivity can be is what is my value at saturation. When I'm less than saturated, my relative hydraulic conductivity is less than saturated. Now, the other thing that happens here is that because at lower volumetric water contents, my smaller pores are the ones that stay saturated. That means that the lower this volumetric water content gets, the higher my tension is. My smaller pore throats can pull water better and better. So my tension or my negative pressure head is also a function. So lower volumetric water content leads to more negative psi. And remember, we called that tension. That's that ability to pull the water out of the soil. So the lower my volumetric water content, the more negative my pressure head becomes. Because I have smaller and smaller pores saturated. All right, so we'll take a quick break here in a sec, but let me, I got a tree here. Here's my water table. I got to do this small. So here's water table. All right. So this graph here is my pressure head. Here's 0 going down past the water table. All right, so this is negative, this is positive. This graph here is my volumetric water content. It goes from my volumetric water content can vary from 0 to n. But there's some amount of pores that are so small that we'll never drain them via gravity drainage. And we call that our residual water content, theta sub r. All right, so we talked about theta sub r already. And then one more graph I want to consider here is K sub r, my relative hydraulic conductivity. And that's going to go from 0 here to 1. All right, and here is my water table depth for all 3 of my plots here. All right, so psi starts negative, hits 0 at the water table, and increases positive. The details here have to do with how saturated I am. So this profile here where I'm the most negative near the surface is like a long time after precipitation. I've been drying and drying and draining and draining, and I have the lowest amount of water content at the surface. All right, so let's plot water content here. It would be here very near the residual water content. At the surface, it would increase until it hit porosity. Just above the water table, actually, is the zone where it would hit porosity. This is the capillary fringe, all right? And it would remain at porosity, 100% saturated below the water table. And finally, K sub r, it would be really low, maybe 0 or close to it here at the water surface because I have very low volumetric water content. And it would increase to 1 near the water table and stay at 1 below the water table. Okay, so there's this relationship between psi and the volumetric water content, all right? And this relationship gets called the water retention curve. Because soil scientists used to be interested and still are interested in how well a water holds on to soil, or how well a soil holds on to water or drains it. All right. So when I come back, well, let's take a 5-minute break. When we come back, let's talk about some ways that we define the relationship between psi and volumetric water content, and volumetric water content. The other relationship here is volumetric water content and the relative hydraulic conductivity. Those two relationships determine how water will move in the unsaturated zone. All right, 5-minute break, use the restroom. Let me pause the recording. Okay. So let's get into the nitty-gritty. So these relationships get called characteristic curves. And they're the relationship between the unsaturated, the volumetric water content and the capillary pressure, or the negative pressure head, or the relationship between volumetric water content and the relative permeability. And so the first one we'll do is this, the relationship between psi and theta sub W, the water retention curve. And let me just tell you that there's a cottage industry of trying to figure out what these relationships look like. You are going to use the two most common in hydrology, all right? And the first is the Brooks, or the first is the, we'll talk about as the Brooks-Corey. And then the second one is called the Van Ganukten. So let's do one thing first. Let's define effective saturation SE, all right? And here, SE is defined as the volumetric water content that we measure, all right, minus the residual water content. And this is normalized by porosity minus the residual water content. Think of this as, all it is a normalized, it takes our volumetric water content and normalizes it. All right, so when my soil is at residual water content, what is the value of SE? So if I go out and I measure this guy and it's equal to the residual water content, what's the value of effective saturation? 0, right? If I'm fully saturated, what is the value of effective saturation? So if I'm fully saturated, what is the value of my volumetric water content? N. So at that point, SE is 1. All right. So SE varies between 0 and 1. All right. It's 0 when I'm at my residual water content. It's 1 when I'm fully saturated. So the Brooks-Corey relationship looks like this. These are empirical relationships. So some of them, like Brooks Quarry is moderately based on some physical properties of the soil, but it's just, this guy Brooks was a hydrologist at Colorado State, and he just had a bunch of these measurements of pressure head versus saturation, and he fit this function to it, all right? And it says this, the effective saturation can be written by psi sub b over psi to the lambda when psi less than psi b, 1 when psi greater than psi b. And I'll define these parameters. Psi b is the air entry pressure. All right, and this is in meters. This is how much pressure would it take to force air into a saturated pore. So how hard would I have to push the water out of the pore? And lambda is something to do with the grain size distribution. Let's look at one of these really quick. Here is one. This is Brooks and Quarry relationship. This is the volumetric water content, all right, versus versus the pressure head here. What you see is that you get these curves, all right, that define the relationship between the volumetric water content and the negative pressure head. All right, so this is what they look like the higher the volumetric water content gets. So this is essentially, this must be porosity of this silt loam must be at about 0.45, right? That's fully saturated. And here my negative pressure head is equal to 0. All right, I'm fully saturated. As I desaturate, my pressure head gets more and more negative. All right. And we would expect that like a silt loam has smaller pore throats. All right, smaller pore throats should have more negative of a capillary pressure. And you can see here that as I desaturate, I'm far more negative here. They hold on to the water better. Whereas the sand should have pretty big pore throats. It doesn't build up very much negative pressure head, all right? I need to become very unsaturated. And the residual saturation is going to be something like 0.05 here. And at that point, I'm really starting to get to, you know, the most negative pressure head I'm going to get here, which here would be something like negative 125. And I'm at negative 125 in my silt loam with still, you know, a volumetric water content of about 0.25, like something pretty, still a lot of water in it. All right, so that's what these things look like. So if you wanted to plot one of these, there's a whole bunch of ways to do that, but just for the Brooks-Corey, what I would do is assume you have to be given psi sub b and lambda, right? So let's say I was using Excel. I would have a column of size that vary from 0, which is fully saturated, to some negative number, say negative, what do we see here on this plot? I saw I don't know, negative 150. Let's just say that, all right? So I would have I'd have a column of size that went by, I don't know, ones or tens from 0 to negative 150. And then I would just calculate SE according to this equation. So I'd have another column that would have the effective saturation, and it would take this psi, and it would take these two values for psi b and lambda, which you have to be given, and it would calculate SE. And it would have to have some kind of logic, so that when psi was less than psi b, it was doing this, and when psi was greater than psi b, it was just setting it equal to 1. Yeah, it totally can. Or, you know, you can also manually look in there and be like, oh, look, my psi's are greater than psi b. I should just set it equal to 1. I would do it with an if function, but it doesn't have to be that fancy. Once you have that set up, you can just plug in a different psi b and a lambda, and you'll get another curve. So really, it's just putting in this equation into Excel. Now, I would have another column so that you can get this effective saturation. These, if we look at these, they're always plotted as psi versus theta sub w. So you can just solve this equation for theta sub w and back out theta sub w. So you would have a column of SE, then I would have another column that solves for theta sub w. And then all I do is plot. I make it a plot in Excel. The Y is my psi column, and the X is my theta sub w column. So the whole point of this problem in many respects is just to get you guys to figure out how to do one of these column-wise functions in Excel. My learning objective there is to force you to use Excel to code up an equation and plot it. Or Python or MATLAB or whatever you want to use, R, I don't care. But Excel is pretty easy. All right, so that's Brooks-Corey. The Van Genuchten equation, it predates Brooks-Corey a little bit. I think Van Genuchten was also a hydrologist at CSU. And his relationship looks like this. And Van Geneuken's equation, Brooks-Corey has some nice features in that psi b is the air entry pressure. You could actually measure that. It has something to do with, you know, and then lambda is sort of loosely tied to the grain size distribution. Van Geneuken is just fully, it's just a fitting function. There's no physics or really anything behind it. So alpha is some fitting parameter. And it has the units 1 over L. It's roughly analogous to the air entry pressure. This is another beta is another fitting parameter. And then gamma is just a simplification of notation. It is 1 over 1 minus beta. So really there's two parameters that we take. If we want to calculate the characteristic curve for a soil type, we're going to make a measurement of a bunch of volumetric water contents and a bunch of air capillary negative pressure heads. And then we're going to fit the equation by adjusting alpha and beta. All right, but this would be the exact same thing. You know, I'd have that column of size, right? Going from 0 to negative 150. And now they would just plug into this equation. C, where's C? This one here. Oh yeah, and I need to close those parentheses. Thank you very much. Yes, ma'am. Let me. Yep. Now, the next one is my relative permeability curves or relative conductivity. K sub R curves. And there's a Brooks-Corey version and a Van Geneuken version. So the Brooks-Corey looks like my relative permeability psi b over psi to the 2 plus 3 lambda. And this is when psi is less than psi b. 1 when psi is greater to or equal to psi b. So same thing goes. You take that column of size, you plug it into this equation. You have another column that just calculates this equation. So you get a series of K sub R's. And this psi b and the lambda are the same variables for the capillary pressure curve or the negative pressure head curve. Van Geneuken is a little bit more horrible to write, but it's a similar idea. It says the relative conductivity 1 minus alpha times absolute value of psi to the beta minus 1 times 1 plus alpha abs psi to the beta times negative gamma. And this whole thing is squared. One plus alpha ab psi to the beta times gamma over 2. All right, so if you do this right in Excel, you could have a column that's all size from 0 to negative 150. That can then lead to a column of SE, a column of theta sub W, and then a column of K sub R. All right, all on the same, it's like 4 columns. And then you can make plots however you want. You can plot theta sub W versus K sub R. Or K sub R versus theta sub W. You could plot negative psi versus theta sub W. And that is what these curves look like. So here's a moisture content. So this is theta sub W versus negative head pressure. This side is the Van Genuchten. This side is the Brooks-Corey, and these dots are the same data. So you can basically just see they're fitting the same data. The curves have a bit different of a shape, all right? We almost always plot it as moisture content as the x-axis and psi or K sub R as the y. And the idea is that we look at how those two variables function as a function of the change in saturation. All right. We're out of time. Homework due Thursday. Feel free to ask questions. Think you have everything you need now. What's that? Oh, we don't have the green amp model. Well, you'll have to look that one up, I guess. It's real easy. Yes, I do. Thanks, Lily. Autumn, I have yours electronically, so we're good.